So trigonometric subs, basically, we are going to make a substitutions, okay, using trigonometric, okay. So it can be sine, cosine, or some other trigonometric functions. For example, let me just start with the integrations. Just 1 over x squared. This is x squared minus 9 dx. So this is what we call the first case, or case 1. Okay. So we have 1 over, and usually it has the square root. Okay, so it has squared and squared minus some constant. Okay. So perhaps if the squared may be just a linear, maybe we can do something on just a regular substitution. But here we have squared and then squared, and then it's in the square root. So this is when we need to substitute the x with the trigonometric functions. Okay. In this case, what we are going to do is we just need some identity. So at least 2 identity that we need to have. I think last time I mentioned. So first is the basic identity. So if we multiply this with 1 over cosine squared x, we get the second identity, which is tangent squared x plus 1 equal, this is secant squared x, right? So trigonometric substitutions is based on these 2 identity. So whenever we have, this is something squared, variable squared, minus a constant, we can see from our case here what kind of trigonometric substitution that can be replaced, okay, for this x, for this x. So this is when if we, for example, here, if we write this in terms of secant squared x, this is minus 1. Okay. If you see from this part, the first one, I think this the first one is a constant minus variable, right? Either cosine or sine. But here we have the trigonometric functions minus the constant, right? Which is perfectly fit with our function on these integrations. We have variable minus a constant. So we need to find what kind of trigonometric functions that can be replaced with this x. Okay. And then you need also to consider the 9. Okay. So consider 9 as 3 squared. Okay, 3 squared, right? So if we, for example, if we take x as, for example, 3 secant, and we introduce a new variable now, theta. Okay. If we getting this, and if we replace this 3 secant theta into x, this will be 9 secant squared theta minus 9, which is perfectly, it can be 9 tangent squared. Okay? So if we are going to substitute this, it's perfectly fit with our equations, right? And then we need to also consider the dx, okay? Because this will be substituted all. So the substitutions concept similar with what we have before, the regular substitution, which we need to remove the variable and change with new variable. Our goal, change x into new variable theta. Okay, so that's our goal. So we can let this derive become dx, secant become secant theta tangent theta d theta. Okay, so we can replace the x with this whole thing here. So we can write down that this will be equal integration I will write dx with this. So I will write on the top 3 secant theta tangent theta d theta over the x squared will be here. So 9 secant squared theta, and then let me just write all 9 secant squared minus 9. Okay. I think we can cancel this 3 with 9 and secant with the secant here. Okay. And then inside the root we have 9 tangent squared theta, right? So it's inside the roots. So we can simplify it further and becomes, this will be integration tangent theta d theta over. This will be 9 tangent squared. Because of the root, we have secant theta. This will be 3 tangent theta, okay? And then we can cancel again. Oh, I have 3. I forgot 3. It's 3, right? It's 3 from 3 here, okay. And then the tangent will cancel this one. So we have 1 over 9. 1 over secant is cosine, okay? So here is 1 over 9. Integration of cosine theta d theta, which is, we can get, this will be 1 over 9 sine theta, okay? But it is not yet complete. Well, it's plus constant, but this theta itself is not yet our expected solutions because we are from the x variable, right? And then we can becoming theta. So what is our goal? We are going to go back to x. How do we do that? How do we do that? We have x is 3 secant theta. And how this relates to our solution? This relates to okay. So suppose that this is let me write. So this will be theta, okay? So what will be the secant theta? Secant theta will be, so let me write here, secant theta is x over 3, right? Or if you're not familiar with the secant, you can just take the cosine, which is 3 over x, right? Which means start from this 3 and this x, okay? And how about the other sides will be, we can take the Pythagorean, and this will be square root of the x squared minus 9, okay? Get it? And now our answer is sine. So what will be sine theta? This over x, right? So we can change directly. So this will be 1 over 9 square root of x squared minus 9 over x. And now I will add constant. Okay. So this is, we call the case 1. Okay, case 1. Case 1 is this the square root x squared minus a squared. A is constant. At least for the trigonometric substitutions, until all the possibility for the identity, the so the case 1 by 1 is based on what we have in this identity. So that is the function that we are supposed to substitute with. Okay. Any question from this part? Quite difficult. You give me the smile that I'm not sure is this difficult or not. Okay, now case 2, and I will just write this example directly. So x cubed 9 minus x squared dx. Okay. Is my writing too small or it's okay, right? Okay. So how about this one? Okay, we have x cubed and then roots 9 minus x squared. Using all the possibility from the identity, choose which one that is fit with the integrations. So the idea is looking at the roots. So this is a constant minus something. It can be two possibilities. It can be two. But the way we solve should be, the final result should be similar. Mm-hmm.
So use for the first one.
Mm-hmm.
1 minus cos squared.
Yes, we can use 1 minus cos squared or 1 minus sine squared. Will be similar result. Okay. Okay, so we can use the first one, the first identity, either using cosine or sine, right? So I think, let me just write using the sine. So let's exchange the x. So let x equal to, because it's 9, so we have 3 sine, okay? So I choose sine because when I derive x, this will be still positive. Okay? But if you check cosine, it should be okay, right? So check the derivative will be 3 cosine theta d theta. So we are going to exchange the dx with this one, okay? Yeah, any questions? Which part? You still feel missing?
Where do you take the relationship base x equals to 3 sin x sine?
From here. So what we need to find from these two identity is, you can imagine the part of the function will be the variable x. So remember, if this is x, if you move here, this will be a constant 1 minus something, right? So this will be constant minus something. That is perfectly fit, right? So it's either sine or cosine. Okay. The same thing with this one. This is a variable minus constant. So the possibility is this, right? Variable minus constant. That's why. Okay. The reason. Okay. So let's exchange this. The x cubed we can exchange with the 3 sine, right? And then cube it's become 3. Just let me write 3 sine theta and then cube. And then square root of 9 minus 9 sine squared squared theta. And then the x will be 3 cosine theta d theta. And then, forget the integration. Integration, this will be still 3 sine theta cube. This will be, let me write. We can write this as 9 cosine squared theta, right? So this will be, because of the roots, this will be 3 cosine theta. So 3 cosine theta, this will be 3 cosine theta. And then this will be, so 3 cubed, and then having 3, we have 3 with power of 5, right? 3 power of, let me write, because that is constant. I think I will factor the 3 out. And then integrations, sine cube theta cosine squared theta d theta. What should we do with this one? This is the last week before quiz. So this is what we call the trigonometric integral. So the idea is still the same. We are going to check within our identity for the trigonometric. How do we suppose to exchange? So basically we are going to just take substitutions. But we need to check and to observe how do we arrange the sine and cosine so that when we substitute one, it will cancel the other one, and then it will change everything from the trigonometric into just a regular u, variable u. Okay? So which means that if we take, for example, the sine squared theta and then cos squared theta, and then write sine theta here, so I'm separating the sine with the sine squared from the sine cube. Okay? So if I write this, and then simply we can try to see which one of these two that we can substitute with the trigonometric identity. So if we substitute the sine squared, we are going to get 1 minus cosine squared theta okay, we get this. So for example, if we substitute the cosine, okay, if we substitute only cosine, let me write with the red color. So if we substitute u as a cosine, so this will be 1 minus u squared, this is u squared, sine, I forgot d theta. And then, as usual, we take derivative of u, this will be negative sine theta d theta. So we can cancel the sine theta from here, right? Okay. So let's change all into u. So let's change into u. So this will be 3 with power of 5. This will be 1 minus u squared. 1 minus u squared. This is u squared. And let me just write sine theta. And then d theta will be du over, or minus 1 over sine theta, and then du. Okay. So this will be cancelled. This will be minus. So minus will be here. So we have u squared minus u with power of 4. Or since this is negative and negative, I would like to change and to make it all positive. So I will exchange this, become this. Okay, same, right? Just to make easier to read and avoid mistake because of the negative sign. Okay, so u power 4, u squared, and we can integrate easily. Okay. But remember, this is u, and then we are going to change back u to theta, and theta change back to x. Don't forget that, okay? So we are not yet finished. Okay. So here we get 3 power of 5. This will be 1 over 5. This will be 1 over 3. And this u is cosine, right? Or let me just get to the left to get more clear. So we get u is, so let me just write here, 3 power of 5. 1 over 5. U is cosine, right? Cosine theta with power of 5 minus 1 over 3 cosine theta with power of 3. And not yet finished. We are going back to these relations. So going back to our triangle here. So sine theta is x over 3. So x over 3, right? And this will be square root of 9 minus x squared. So cosine will be this over 3, right? So change everything. So this will be 1 over 5. Or this can be written as 9 with half, right? So I can multiply with 5. So it will be 5 over 2. So 9 minus x squared over 5, with power of 5 over 2 minus, this will be 9 minus x squared. This is 3 over 2. Okay, I will just stop here, okay? You can further compute with the constant, but I think I just stopped there. And forget plus constant. Plus constant at the end. Okay. Okay. Complicated? Yeah, the trigonometric part, right? Okay. 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 But I think the important part is the first trigonometric substitution here. As long as you can identify this from these combinations, it's supposed to be okay. So whenever you see any square root with something inside that is either variable minus something or constant minus the variable, perhaps you need to check with the substitutions, okay? With the trigonometric substitution. Okay. And of course, how do we apply that in exam? Which method should we use, right? So that is, I think, one way is to experience by your hands. First experience. There is some like guidelines, like for example, you can think the regular substitutions and then think with some other methods. And if that's not works, then you need to perhaps to specify the specific methods, like this one or another one. Okay.
Why don't we divide it by 3?
Hmm?
No, the triangle.
Oh, here? From here.
Yeah, but if we find cosine, we have to take square root of 9 minus x squared over 3.
Oh, right. Good. Okay, just adding 3 over there. Okay. And I think this will be, wait, this will be 3 power 5, right? This will be 3 power 5. This will be 3 power 3. I think we can maybe further simplify it. Three. Okay. I think it should be okay, right? Okay, can I erase the left one? The left one, okay. So this is case 2, which is the constant minus the variable x. So let's go for another case. Now we have x squared plus 9, okay, dx. So this will be the constant plus the variable, so case 3. So an x plus the constant a. So of course, if we look on our identity, this will be perhaps the most plausible way. Okay, for the x squared plus a constant, it will be best if we replace x with the tangent, right? So again, we can simply let the x, okay, replace with the tangent. Or this should be 3 tangent theta because it has 9, right? So the x is 3. What is the derivative of tangent? Is secant squared theta. D theta. So this is for dx. Dx will exchange here. So we can exchange everything. So let's change everything. This is tangent cube theta. And then this will be 3 secant squared theta, d theta. And the below is the 9 tangent squared theta plus 9. So 9 tangent squared plus 9 is 9 secant, right? This is 9 secant squared theta. So if we take the square root, it will be 3 secant, right? 3 secant. So this will be tangent Oh, wait. This should be 3 tangent. So 3 cube. So let me write maybe 27 over here. So this would be tangent cube over 3 secant theta, and then this will be 3 secant squared theta d theta. And just cancel and cancel. So we have tangent cube theta secant theta d theta. And what should we do for this one? So we have tangent cube and then secant. And again, we can relate to the substitutions for the identity for tangent squared plus 1 equals secant squared. So again, this will be also trigonometric integrals that we did last time. So we can let the arrangement for the equations become, so this is 27, this will be, so let me just take the tangent outside of the cubic. So let me just write tangent squared and then secant theta and then tangent theta. Okay, so here we expect to cancel the secant and tangent. So we are going to change the tangent squared, become the secant squared theta minus 1. And if we let the u equal secant theta, it will also cancel the secant and tangent, right? So if we take this, and let me write here. So this will be secant squared theta minus 1. And this will be secant theta tangent theta d theta. So if we let u is secant theta, du will be secant theta tangent theta d theta. Okay. So we can take that and exchange everything, become u squared minus 1. And this will be cancelled, so this will be du. Okay, so let's integrate. So integrate. So u squared become 1 over 3. And I will change u back to the secant. So this will be secant theta cube minus u. U is secant theta, so secant theta. Okay. And again, this is still secant theta. We are going convert back to the x. Okay. So we are going to revert back by taking the triangle. So this is theta. So tangent theta is x over 3. So x over 3. So this will be x squared plus 9. We have secant. Secant is, or if you want to start with cosine, so cosine is 3 over square root of x squared plus 9. And secant is, we reverse this, become x squared plus 9 and over 3. And change everything back to the x. So 27. So this will be 1 over 3. X squared plus 9 with power of 3 over 2. 3 cubed is 27 minus. This will be x squared plus 9 half over 3. Or we have 1 over 3 should be 9, and this is half plus c. Okay, yeah, that's the case 3. Okay, any questions? Yeah, the trigonometric part is a little bit complicated. So it's not like direct approach to solve the problem, but it has, or it contains many more problems inside. Yes?
How do you choose which strike one or two substitute?
It's based on these two identity. Okay? So you need to observe this and then compare with the questions. Which one is the most suitable one? Okay. So I don't want to say like if you do this, then substitute with this, but you need to check by yourself and make sure that when you do that, you are convinced yourself. Okay? For example, we have the variable plus constant. So check which one is the most possible way. I think only this one, right? So that's why we change the x into this tangent. Okay. Okay. All the case, like case 1, case 2, case 3, I give you the direct or obvious choices. Okay? Sometimes the question may be given something that you need to arrange first to make into this and then substitute with the trigonometry. Okay? So that's the one that I will give you some example on that. Okay? So this part, like the technique of integration, is the last part in our sections. It contains all the techniques you need, including the integration by parts, the trigonometric substitution. After this, we have the partial fractions. And the last one will be the improper integral. Okay? So we can integrate with something that has infinity inside. Okay? It can be the endpoints, can be infinity, or if it has any discontinuity, we can approach the integrations with limit that we can basically evaluate and compute. Okay? So my goal today is this method and introduction to partial fractions. Partial fractions is, I think, is actually quite simple. Do you want to take a break, or we go and then I will end around 10:45? Do you want to go or take break? Go? Go? So we will finish 10:45, okay? 10:45 is okay? Okay. Like, I just want to make sure. Because I know that it's Saturday, you want to finish early. Yes, sure. What do you want to ask?
I understand that he will replace it with this because this is a triangle, so x is 3.
Yeah.
But why did you change 1 for this?
Okay, from dx. Not 1, dx. You have dx.
dx here.
Yes. Yeah. Okay. Okay. I think we can move. And I will end around 10:45. Okay. Okay. Okay, how about that? We have integration of that. Okay, try this one. It's supposed to be with trigonometric subs, but you need to do something first before doing the substitutions. Yeah? Up to you. Up to you. I think this will be like worthy to be in the exam. Well, of course, in the exam, I will make it balanced. Something that is difficult and something that is expected to be done. Okay. Any idea to solve this one? The clue. Complete the square first. Complete the square, and make it into like, this square. Yeah. I think complete the square. That's the clue. And rearrange the constant and the variable, and you will see that we can substitute that part. Okay, so to solve this, let me just focus on the quadratic part here. Let me write over here. So I will write 3 minus, and I will make a bracket, and this will be 2x plus x squared, or let me write x squared first, okay, to make it easier to see. So x squared plus 2x, okay? So to complete the square for the x squared and 2x, we need to plus 1, right? So let me equal. So if I'm going to plus 1 here, this will be minus 1, right? The minus in front of the bracket make this 1 become minus. So I need to plus to make it equal, right? So I need to plus, maybe I will put 1 here. Okay? Just a regular complex square, right? So this will be 4 minus, and this will be a perfect square, x plus 1 squared. Okay? Right? Okay? Sometimes if you are not convinced enough, you can break down this and then check whether it's going back to the original one or not. Okay? So check, if you want to check, you can check. And I think this 1 is minus, so it's 3, right? 3 minus that, right? Same. Okay. So let's change the structure. Okay, let's change the form. This will be equal. So x, this will be square root of 4 minus x plus 1 squared, and then the x. Now you see, okay, now you see this. You can observe that this constant minus variable. Okay. We're going back here. A constant minus variable. So it could be this one, right? Okay. We can substitute with cosine or sine. Okay. And before that, since we are still in the x plus 1, maybe we need to substitute first, okay, with regular substitutions to make it more clear and make it something similar to this, right? Variable, perfect variable, and constant. So since we have this x plus 1, so we can substitute first with, let's say u, okay? We can substitute with u. So let me write here. So let's just substitute with x plus 1. Okay, so x plus 1 is taking u, it's x plus 1. Du is dx. But how about x? X is u minus 1, right, from here. Okay, we can take in that substitution. So we can substitute everything. And becomes integration u minus 1. This will be 4 minus u squared du. And now we have a clear equations that we can substitute directly with our trigonometric identity. Okay? So a constant minus variable. Okay? So here, so it can be cosine squared, or this also can be done. So either sine or cosine, they will produce similar results. Okay? Or even if it is not the same, it will going to be the same because of the difference in constant. Okay? Sometimes, like if you have choices between sine and cosine, the end result sometimes it will be the same, sometimes it will be different in the integration. But the differences usually they will make up because of the constant here. Okay? So because of the constant, they may be the same. Okay? Okay. So let's substitute this with let let me write here. So let u is 2 sine theta. Okay, 2 sine theta. So du is 2 cosine theta. So substitute everything. Here will be, let me write over here, 2 sine theta minus 1 over this is 2 cosine theta. I'll forget the theta. Okay. And this will be equal. Let me write integration and give brackets here. This will be 2 sine theta, right? 2 sine theta. Or 2 cosine theta, sorry. So 2 cosine theta. And this will be 2 cosine theta. Theta. So we are going to cancel this. And then we just have 2 sine theta minus 1. And we can integrate easily, right? Sine theta integrate will be minus cosine. So we will write minus 2 cosine theta minus theta, right, from this one. Okay. So again, we need to go back to x. So from theta, go back to u, go back to x. Okay, so here we have a triangle. Theta is here. So sine theta is u over 2. So u over 2, this will be 4 minus u squared, right? That would be this cosine theta. So minus 2, 4 minus u squared over 2. So I think I will just cancel this 2. So then minus theta. What is theta? Theta is, let me write maybe here. So from this sine theta, so sine theta, let me write, is u over 2. So theta is sine inverse u over 2. Okay. Okay. So today's overload with the trigonometric, right? So if you think, oh, maybe we don't need trigonometric, we are having a lot of trigonometric now. So this will be our solution for u. U is x plus 1. So we change back. Change the color. So 4 minus u squared, this is actually our question. And this is the same. So we can change back to this one, right? So this will be negative 3 minus 2x minus x squared minus sine inverse of u is x plus 1. So x plus 1 over 2. And then don't forget plus constant. Okay? Crazy, right? Trigonometric with steroids. Huh? Yeah, just these two. Just these two. Okay. Yeah, it's so hard. That's why it's like it's worth it to be in the exam. Right? Okay, any questions? Question? Oh, that one? from here. This one is actually this one, right? And this one is that one, right? Right? Well, if you want to do the step by step, it's okay. Like u is x plus 1 squared, and then going back to that. But I just see that this is actually the same, so I will just bring back the original one. Okay? And so I think I need to give you more, maybe some example and practice. But I think I will just prepare first what will be the questions. Okay. Yes?
Okay, so I get how you get this triangle, right?
Yeah.
Because this, and then
From
this,
here,
this.
Mhm.
And then what do you do after that? This or this?
No, this will be for this theta. Theta will be based on this one.
Yeah.
Yeah.
And then what do you do after getting this triangle?
Getting this triangle?
Yeah.
Just solve the integration. So solve the integration. So the triangle is for how to relate the theta to u to x. That's the. So if not using the triangle, we are not going. No, we are not knowing how to convert back to x.
All right.
Okay, can I erase this part? This part? Okay. Okay, so I will hold this trigonometric subs for a while. I will give you more practices, maybe next time in class, or maybe just like a practice at home. But I would like to just introduce another section, which we call the partial fraction. Partial fraction is actually how do we separate a fractions and make it into smaller fractions. So like we have a big fraction and we separate with a small fraction. For example, let me write first. This is, we call the partial fractions. Okay, so suppose that we have, let's say, this fraction, and then maybe we have a minus with this, okay? So I think like what you did in junior high, right? Partials like this, junior high or elementary school? Junior high, right? Elementary school is just a constant, right? So if we have this, then we can multiply the denominator like this, right? Okay. And then put back here, and we have 2. Okay, and then we can continue. So 2x minus x is x. This is 4 plus 1 is 5. And then we have x squared minus x plus 2x. So will be plus x minus 2. So we have this, right? Now our goal in partial fractions, if we have an integrations with that fractions, We don't know how to integrate that directly, right? Unless if we separate this, become this, then we can integrate each one of them easily, right? So that's the goal, okay? The goal in partial fraction. How to separate like big chunk of fractions and make it smaller fractions that we can integrate easily one by one. That's the goal. And there are several ways and several cases. And I don't think we need to know or at least to memorize everything. I will just give you like how to identify directly. So there will be some like a summary method that I will give to you. And maybe if time is not sufficient, maybe in the next class I will give you more details and examples. So basically, if you want to take partial fractions from this one here, suppose that we don't know this, right? Suppose that we don't know yet. Okay? What we do is, if we can factorize the denominator, then we can factorize first. Okay? So first we factorize, and of course since we have this factor, so we know that this will be x minus 1, x plus 2, like that. And then simply we are going to take this, each one of them. And then we suppose that we don't know yet whether it's plus or minus. We just write plus. Okay? And then this will be 1 x plus 2. Oh, using bracket here. Okay. And then we take constant a and constant b. Okay. And now, simply we do the same thing as we did here. So we getting by the denominator. So we are going to have, this will be that. And this will be a multiplied with x plus 2 plus b multiplied with x minus 1. Okay. And the top equation will equal to x plus 5, right? So let's equal this to, so the ax, or maybe I will just combine everything. Ax plus 2a plus bx minus b is equal x plus 5. Okay. So this will be, I will group all variables, the same variable. So a plus b is x plus 2a minus b. Okay, now what we do is, we look on the same groups with left and right. Okay? So this is x, this is x. So a plus b is 1, right? Okay. And the constant 2a minus b is 5. Okay. And then simply we solve the system of linear equations. So basically, the partial fraction is a part on system of linear equations. Okay. Now we solve this, and let's say we plus this 2. This will be 3a equals 6. So a is 2. So because a is 2, then b is minus 1. If we take a here, so b is minus 1. So we get that this 1 will be 2 over x minus 1, and b is minus 1. So, or you can write plus, and then this will be minus 1 like that. It's okay. Or if we change this to here and it become minus, and it's supposed to be the same, right? Okay. So that's how we do basically. Okay? But there will be some cases, okay, in the partial fraction. For example, the factors. Okay? When we factorize, maybe the factors have some multiplicity, and because of that multiplicity, we do have some certain of property in partial fraction that can help you to easily separate the functions. Okay. some kids. Okay. Another case that I think you need to be also obvious. You need to check the degree, okay? Degree on the polynomial. So, if, for example, if we have example, if we have integration x cubed plus x over x minus 1, what should we do? Of course, it's not partial fractions, not directly partial fraction, but it has something to do with partial fraction. So if this, like, this is having a cube, and this is a linear. So let's rearrange the structure. Rearrange the structure as in polynomial. Like we have the polynomial division, if you remember. So we just take the long divisions. Okay. So this will be what? X squared. X squared, x cubed minus x squared. So minus. So 0 minus minus, so x squared plus x, right? And then plus x. This will be x squared minus x. This will be minus plus 2x, right? 2x. And then plus 2. So there will be a reminder, right? Hopefully you still remember that part on basic of math. So 2x minus 2. So this will be a remainder of 2. Right? Which means that with this structure, we can rewrite this. Becomes the x squared plus x plus 2 plus the remainder 2 over x minus 1. Okay? And we can integrate this, right? We can integrate this easily. So if you integrate, this will be 1 over 3 x cubed plus x squared over 2 plus 2x plus 2 ln x minus 1 plus c. Okay. So the first one here that we did here is we call this as, so since this is, we can completely factorize and the factors is different, no multiplicity. So this is, we call the case 1, or let me write with red. So this will be case 1. We call case 1 as a distinct factor. Each factor, they have their own structure, okay? So each one they have, and then we can separate one by one, and we can integrate one by one. However, if we found multiplicity in the factors, we call the repeated factors. And we have some theorem that can help you to simplify the solutions. Okay, so let me write maybe here. Let's see, still have something here. So case 2, we call the repeated linear factors. So what is linear factors? For example, I give you the x cubed minus x plus 1. And suppose that we have x squared like that, and then x minus 1 cubed. So x squared is multiplicity, x with x. This x minus 1 cubed also multiplicity, x minus 1, and repeated 3 times, right? So how do we separate the fractions easily? Okay. So let me give you the idea. Okay. So first is we can simply see that. Oh, let me write here. Maybe just take the fractions only. So we can see that the first one we have the x squared. The second one we have the x minus 1 cubed. Okay. And since this is squared, we have a linear here, right? Or let me write with the red one. And we have a cube, so we have a quadratic here. So let me write cx squared plus dx plus e. But it's not simple enough, right? It's not simple enough. So we would like to separate more, because this is another way we see that we can separate. So the c, d, and e, we can separate each one by one. So finally, if you are trying to simplify that, we are going to have this. Actually, we can separate one by one. So we can separate this with x, and this will be, I'll give you the practical way first, and then we can see how it works. This will be x squared. So we have five different fractions. This will be x minus 1. This will be, or let me make space over here. So this will be x plus x squared plus x minus 1 plus x minus 1 squared plus x minus 1 cubed. So we have 5 different fractions. And if this is taking only, we call, if you see only without the power, only this one, the x is inside, the x itself is not a polynomial degree greater than 1. They are all linear vectors. So if that is linear vectors, then all the numerator become just a constant a, b, c, d, e. Okay, so this is a linear or a repeated linear factors theorem. So we could like take the fractions more, and instead of just having this separations, we could take more separation into this one. Okay. Okay, and then how do we know the A, B, C, D, E? Exactly as this one that we did before. We can find through a system of linear equations. So we could take, for example, we multiply everything and then divide, and then we have the a. So a will be multiplied with the x and x minus 1 cubed, right? And then plus b, because b is x squared, so b will be multiplied with x minus 1 cubed, like that. And plus c will be that. I think I will. And plus d will be x squared, x minus 1, and plus e, and e is x squared. So we are going to solve this, and then equaling to the x cubed minus 1, minus x plus 1. Okay. Okay. Wait. So this is case 1, case 2. Let me just add another case 3, and then we are finished. Okay. And more example, I think in next class, okay? So case 3 is we have the irreducible factor. So what is irreducible factor? So if we have px over qx, if the q is, let's say, the quadratic functions, and then the discriminant, which is b squared minus 4ac, if this is negative, which means this will be having a complex roots, right? So we have complex root. Or in the real number or the real world, this will be then the a x squared plus bx plus c is, we call, irreducible. Okay. Which means if, okay, example, if we have a fractions like x over if you have this, then these two parts, we are not going to take this as our linear factors. Okay? Our linear factors is something like this. This is all linear factors. Okay? X squared, it has squared, but we can think like x on the x itself. That is, we can treat them as linear. So linear with the factors. But here, we cannot do anything, right? We just see that this is just x squared plus 1. We cannot like take out the x and factors. So we call this 2 as irreducible. And what does that mean in our partials? So when we take the partial fractions, so first is linear factors. It's the same like before. But the second one, we need to take all the irreducible factors, the x squared plus 1, and the rest, that the numerator becomes linear equations. Okay, so this will be dx plus e. Okay. And actually there are case 4 in which the same as with this, but the irreducible can have a factors. for example, if we have like, for example, we have this 2, for example, it means that we have another additional fx plus g. This will be x squared plus 4 squared. Okay. I will review again all this part, case 1, 2, 3, 4, with example. Repeated irreducible factors. Okay. Seems a lot, but it's actually not that difficult compared with the trigonometric subs. I still consider trigonometric subs more difficult than this one. This one is, as long as you can separate the fractions, should be okay. Should be okay.